today's lesson, we're going to take a look at quadratic models. So if we go back a little bit, remember linear models where we had this equation y equals mx plus b. And we know that b was the beginning spot and m was the slope or the steepness of the line. Well, what we're going to do is we're going to build our quadratic model today. So we're going to start with this linear model and we're going to build the quadratic model. So we'll use y again as our variable. And the first thing we notice with the quadratic is that we still have a beginning value. This b gets turned into a c. It's still the beginning value, or the y-intercept. We just use the letter c now. The mx part continues down to our quadratic model. We just call it bx now. And it's still the initial slope, or the rate of change. We just use the letter b. So this part of the linear model that we're used to actually is sitting in the quadratic model right here. This is the new or defining part of the quadratic. It's this ax squared part. That's the new part. So let's investigate that. The best way to think about it, I think, is with baseball. Imagine hitting a baseball. We know we have an initial height, c, and we know when we hit the ball, it flies off at a certain angle, or that slope, or that initial value. That's the bx. We're used to these kind of things. So it could go like this, or it could be a little bit higher, like a super high, like a pop fly, or maybe just almost horizontal. In theory, it could actually, go negative too if you sort of hit the top of the ball. But we know in baseball, once the ball is hit, it goes up, but then as always, it has to, of course, come back down. Okay, so it flies through the air and then it has to return back down to the ground. And that's the new part of the quadratic. The linear model gets it going, that we're used to, but the quadratic, that new part, curves it back down to the bottom. So we start with our linear part. We have an initial height and an initial slope. And when we add that new part, actually our straight line actually gets bent into a new line. And that new line is called a parabola. So here are some examples. Imagine you're playing baseball. You could hit a short little shot to there, or maybe a little farther to there, or maybe have a really high hit and it lands there, or maybe hit it kind of high and it lands way over there. These are all versions of parabolas. Now in our baseball example, this new part obviously has a name. And we ask ourselves, what is causing the ball to come back to Earth? And of course it's gravity. So the quadratic equation in standard form is written like this. And this equation creates a special curve called a parabola. C is the starting value, okay, where we start. Bx is that starting direction. It's kind of like initial slope. It's like, the force of hitting a baseball. It's like an angle of hit off the bat. You can think of it that way if you like. And this ax squared, this is the dominant part. This is the new term. Now with projectiles, we call this gravity. But just in terms of the general equation, we see that the x squared, it's obviously a higher power than x to the 1. So this has more influence on the model itself, this part, because it's squared. So this part creates the quadratic function. It controls that bend to form that overall parabola. So again, imagine football. We have an initial height when you throw the ball. We have an initial speed. And of course, gravity pulls the ball back down to the ground. And it creates this, you have the height from here, you throw it, and then gravity pulls it back over. Now, as it turns out, all projectiles are subject to gravity that follow this path of a parabola. And this path can be modeled using a quadratic model or a quadratic equation. Okay. A basketball through the air. Okay. Another example of a basketball here, flying through the air. Kawhi, of course, he was thinking about quadratics when he made the shot. This skater dude. If you are a snowboarder flying through the air, you actually follow the path of a parabola. If you're a trick motorcycle rider, you also fly through the air, subject to parabolas. So it's pretty interesting where we see it all over the place. Now in construction, we see examples as well. If you construct something in the shape of a parabola, it will be structurally sound and actually resist gravity. So horizontal bridge sections are actually difficult to keep stable, as we see here. But a bridge with a parabola for support can span great distances and not collapse due to gravity. So this parabola, because gravity is pulling it down, the bridge itself actually pushes back up. The arc pushes back up and keeps this roadway safe. That's actually Newton's third law, and you'll study that in physics. In St. Louis, they just built a big parabola. If you've been on a roller coaster before, okay, these coasters take those shapes, and you can see it, and once you start looking for it, you can see it in design, construction, in buildings. The garden hose example is always a good one. If you have the garden hose in the summer, you know, the water is subject to gravity, so that arc is actually a parabola as well. Now, I think the best way to examine this quadratic in analytic form is to use software. So we're just going to kick in the Desmos here. And I have a quadratic here, ax squared plus bx plus c, and I've made a couple of sliders. So the first one we're going to look at is c, which is the last value there. So there's our c. And as I move this left and right, the number gets larger, 5, 6, 7. This is where it's hitting. There's 8, c is 8, it's hitting at 8, it's hitting at 9, there it is up at 10. So c, that last number, just like a linear equation, just moves it up and down. That's all it does. Okay, so let's put it right about there. B, this is the bx part. This is that slope part I was talking about. Now as b gets larger, it looks to get kind of steeper initially. Okay, it's getting steeper sort of right off the bat, steeper and steeper. And as I decrease b, it's getting less steep and less steep and less steep. So you can see that. Imagine hitting a baseball higher in the air. It's going higher because it's steeper, or maybe you don't hit it as high, so that sort of controls that initial direction. You can make it 0. If I bring it down to 0, that would be horizontal. And I could actually make b negative, which would then have you hitting the ball down into the ground. Okay. Now here's the ax part. I'm going to have a as negative for now. Don't worry about that. We'll talk about that later. But just look at the value of a. You see how as a gets bigger, so a is now 2 or 3 or 4, there's way less distance traveled, and it tightens itself. The curve tightens up more. This is like me increasing gravity. If you hit a baseball like this, and I said, okay, gravity is getting stronger and stronger and stronger, then the gravity would pull the ball back down a lot quicker. If I made gravity like a value of 3, it wouldn't go as far, or a value of 4, it would be even tighter, and so on, 5 and 6. Like I said, eventually it would really, really tighten up that path. If I could do that, if I said, okay, let's make gravity less and less, so imagine you hit the ball and there's less and less gravity, well, the ball would go farther, the ball would go farther. If I made it interesting, if I made that positive, then gravity, if I could reverse gravity, it would actually take off in the other direction. But we'll talk about that later on. The idea is just to see that this factor up front, ax squared, that's controlling essentially the shape of it. So this is basically the control of the curve or the bend, that ax squared, the quadratic part. B is just that starting value. B is just that starting steepness that we see. And C is just the up-down part of the function. So just in summary there, a basic for parabolas, they have a line of symmetry that split them in half. The line of symmetry of a parabola divides a parabola into 2 equal halves. And at the intersection of this line is what we call the vertex. So basically the vertex is the turnaround spot for these parabolas. So what I want you to do is I want you to go in the Desmos and I want you to continue with this analysis of a quadratic model in standard form. So type this in and then just change those values of A, B, and C and see what happens. Okay. Once that's finished, there's a few questions in the textbook you can try. I want you to use tech for that. I think the book says draw it by hand. Don't. Okay, use some technology, Desmos or a graphing calculator will do. I'll put these questions posted on our website as well. And then we look forward to our next lesson, where we will formalize these changes. So I know I went a little quick there with Desmos. I just wanted you to understand what all the parts were, but we're going to have to formalize that and control it a little bit better using algebra, and we'll do that next. Okay, that's it.